All right, dude, we are live. What's up, guys? This is Dem Keys, and today, we are gonna get back to learning about feed-forward neural networks. Um, yeah, dude, I've been busy with a bunch of research and a bunch of other work, because of which I wasn't able to stream. Dude, I need to get the TTS program up and running like soon. Um, I don't know. Maybe I could build it on stream. I guess I'm not sure. Um, I think initially I'm going to be testing it out within a Kaggle notebook, and then later on, I'll move the code over to like a standalone application. Once the code is completely, ready, then I can move it over to a standalone application. Though actually, I think I might need to move it. So okay, there's a couple of different like components to the program. So there's going to be obviously the TTS itself, right? The TTS model running, but there's also going to be I'm going to be using WebSockets to do the communication between the program that's going to be running on another system from which I'm going to be sending in the text, and this program. So I'm going to be using WebSockets to communicate between this program and that program that's running on another system on the network. Um, so I mean, I can't really test that using Kaggle notebooks. I'm going to have to actually set up the standalone app in order to do that. Another thing I needed to look into was I remember multi-threading and what do you call it? What do you call it? So like in Python, in terms of doing multi-threading or multi-processing, I think these are two of the main options that we have: multi-threading and multi-processing. I don't remember what it's. I think it's called multi-processing, but the gist of it is one involves using multiple threads but from the same process, and the other involves creating separate processes in order to offload the work onto them. And I need to read up on how effective multi-threading in Python really is, because there is that concept of the global interpreter lock, because of which apparently multi-threading isn't exactly multi-threading. I don't fully understand the concept around it. I need to read up on how this makes multi-threading not as effective. And I also need to read up on whether this would greatly impact the performance of multi-threading. Because if it won't greatly impact, then I can just use regular multi-threading. But if it does impact, then I'm probably gonna go with multi-processing instead, where there's multiple processes that are handling this stuff. But yeah, we're gonna need to use multi-threading because running. Actually, okay, hold on. I just I just realized something. Maybe I'm looking at this in the wrong way, because the input is never received from the input is never received from the main system. The input is always received from outside, right? So this okay, let's try to set up a loop kind of thing here. Give me a second. Okay. Well, not a loop. I mean workflow. So the workflow is going to be something like this. Um, program. I don't think I need to write program. So receive input using WebSockets. Okay. And then we add that input to the queue. Um, Wait, okay. So how is this supposed to be running? Because we need to go back and like keep. So okay, once input is received from WebSockets, it's going to call that receive function, right? So at that moment, we can do something with it. But then we also need to have a sort of loop running, which constantly which constantly checks if there's any item in the loop, right? So we have the input side here, but then we also have a loop running um, to check if there are any. No, wait. Loop over Q if Q is not empty. Actually, we shouldn't do that. No, it should be an infinite loop. Infinite loop. Infinite loop. Um, check if Q is empty. If not, process next Q item. Okay. So then that's going to run the model and it's going to do its thing. In that time, we're going to be checking if. Now, here's the thing, right? We don't want to block the main thread, like ever, because that can cause problems. Right now, I don't know if WebSockets would be running in a separate thread, or if it's running on the main thread. Let me check. Hold on. Um, Give me a second. WebSockets Python multi-thread. Okay, so first things first, I need to find the WebSockets package. So let me look for that real quick. Now there is a WebSockets package. I don't know if it's actively being maintained, so let me just confirm that first, and then I'll I'll open it up here. So there's something called WebSockets something. Oh yeah, okay. This is actively being maintained. Library for building WebSocket servers and clients. Okay, let's open the thing up here and then I can read it here. Holy shit, I almost clicked stop streaming. My God, I was supposed to switch to BRB, but the moment I opened up, the moment I brought up the OBS window, my mind literally went towards the stop streaming button because it's blue, I guess, instead of clicking on the transition button, or what is it called? Yeah, transition. Okay, so Python web sockets. I should probably also be mindful of the time because I do wanna um, I do want to do the research. I do want to continue with the neural network research that I was doing because I've gotten distracted with a bunch of different things. A lot of it involving electronics. So I'm not really complaining about it because, this was also something that I had been meaning to do. I still have to place an order for those optocouplers, and I think two or three other things as well. One was the optocoupler. There was also ultrasound sensors because I looked into. Give me a second. Okay. Yeah. So opto op, words optocouplers. That's one that I need to order. That's one item that I need to order. Then there's ultrasound sensors because I was looking into like robotics stuff, and I definitely want to get into the computer vision side of things using ESP32 CAM and stuff like that. But I also understand that doing computer vision stuff is going to be fairly heavy. It's going to be heavy on a PC, let alone the fucking ESP32. So I do need to be mindful of what situations I'm using it in. And if we are talking about situations like, I don't know, detecting the ground, for example, I feel like ultrasound sensors would do a better job of that. So, in terms of what should I call this, movement or path tracing, path building, just movement. In terms of movement calculations, hold on, yeah. So in terms of movement calculations, I feel like why does this look like this? So I loaded up this page and okay, give me a second. Just a minute. I need to look up something. Okay, just a minute, just a second. So what was I saying? I'm doing something behind the scenes right now, which I don't think it's gonna show up anyways, but like I cannot switch away from just a minute. Okay. All right. What was I what was I saying? I remember I was talking about using ultrasound sensors for like path tracing, path building, basically movement calculations, detecting not just obstacles. Definitely, I want to detect obstacles as well, but I also want to detect if there is actually ground for the thing to walk on. And also, speaking of the thing walking, I was also looking into like different types of um, robotics platforms, simple robotics kits, which involve like wheels and motors and stuff. So I have some kind of thing um, that I can drive around, and I was also looking into like cheap robotics toys, stuff like a robot dog, for example, or a robot cat, or basically anything that has like four legs and can walk around and optionally even turn around. Once I have like those mechanical features, then I can hopefully hack the circuitry to make it do other stuff. Or rather, I can hopefully hack the circuitry to control it using an ESP32. Um, yeah, okay. So we're looking into this. Right. So WebSockets is a library for building WebSocket servers and clients in Python with a focus on correctness, simplicity, robustness, and performance. Built on top of async IO. Okay. So this is an important thing to keep in mind. Built on top of async IO, Python's standard asynchronous IO framework, the default implementation provides an elegant coroutine based API. An implementation on top of threading and a sans IO implementation are also available. Where are those? Give me a second. Let me open this up. So, okay, I don't really need this to be multi-threaded, so I don't need to worry about this being multi-threaded. However, this running is a pretty decent reason for why I wouldn't want the main thread to be blocked. Because initially I was going to be like, okay, you know what? It's fine if the main thread is blocked. But then when you're continuously expecting, or when you're expecting to continuously receive input, and you need the thing to be ready to receive input anytime something is coming through, you kind of don't want the main thread to be blocked. Because the thing is, I don't know if it's like, if something is supposed to come, if something is supposed to be received over WebSockets, and the program that's supposed to be receiving it is currently blocked, is it going to be like buffered somewhere? Is it going to be stored somewhere temporarily? And then the moment the program is responsive again, then it's going to like pull the data from there. Basically, I'm not sure if the OS is going to kind of hold it somewhere for some amount of time, or if it's just going to discard it. So I don't want the program to be blocked at all. Which means if we are running ML models, we need to run them on different threads, or maybe even in different processes, but it needs to be on a different thread. A different process is basically a different thread. And I need to see if we can get away with simple multi-threading in Python. Or, dude, you know what? I need to, real quick, I need to write a list that, actually, I think I already have a list. Current stuff to do. Yeah, because I might forget about this. Python multi-threading versus multi-processing. I need to look into both of them so I can decide which one works best. for my purpose specifically, look into GIL. Then I need to look into. There's also Git. I need to finish reading up on the Git protocol and how to set up a very simple no authentication kind of server, because it's going to be on a local network. The whole idea here is to set up a Git server on one system where the repo is going to be residing, and then from any other system on the network, I should be able to pull and push. And I can do this without authentication because this is all going to be local. It's a local network as well, so I don't need to worry about, someone coming in from the outside. So I want to set that up as soon as possible because there's a couple of projects that I need to do that I've currently put on hold because I didn't have this knowledge yet of setting up a Git server. So I need to do that. But yeah, okay. Um, Finish reading the Git protocol and no auth server stuff. What else? Then there was electronic stuff that I need to look into. Yeah. Okay. Um. Oh, yeah. Set up a TTS program. Look into well, yeah. Look into multi-threading versus multi-processing. Actually, I should do use multi-threading or multi-processing. Um, Store. This is another important thing. Yeah, yeah. Okay. So I need to set this up as a separate thing. Look into storing Hugging Face models and weights locally and running them locally. So this way, each time I start up the program, I'm not going to be re-downloading the weights. That's kind of important to not have to, well, not the model specifically, because if the model is already, if Hugging Face Transformers has support for the model built into it, that means the model has been defined within the library already. So I don't need to download the model. What I need to download is the weights. And then each time I run the model, I need to tell it where to find the weights from. So it's not re-downloading the weights, because sometimes weights can be massive in size. Uh, yeah. Okay. So use HF transformers for the TTS. Use, and this should go up here, use WebSockets to receive input from another machine on the network. Okay, cool. Great. Now, we are going to move on from this. I need to do research on this as well. But for now, we are going to move on from this. Actually, I need to write down this thing as well. Dude, we need to get into doing ESP32 stuff on stream. Even if it's like basic stuff, we need to get into doing ESP32 stuff. In fact, not just ESP32 stuff. I think like very, very basic analog electronics stuff. I kind of want to do that on stream as well, just to kind of like refresh my knowledge of very basic analog electronics, but also to learn more about analog electronics, because I feel like there's quite a bit of stuff that I don't know. Stuff like calculating capacitor related stuff, doing calculations when there are multiple power sources involved, how to set up a circuit in which there are multiple power sources involved, and each power source or voltage source or current source is powering a different portion of the circuit. How do you keep all of them separate while still having all of them in the same circuit? And just in general circuit analysis. So yeah, yeah, I need to add that to the list as well. Analog, electronics, basics, maybe do it on stream. Oh, and then also ESP32 streams. Because, dude, once we get into doing ESP32 stuff along with robotics stuff, there's going to be a whole lot of stuff that I can, a whole lot of projects that I can work on. And I kind of want to work on them on stream. I feel like that would be a fun thing to do. Yeah. Okay. So let's move over to what we were supposed to be doing today. Now that we are 27, 28 minutes into the stream. So what we're going to be doing today is going back to the research that we are doing on feed-forward neural networks. More specifically, since we already know how to build, test, and or well, build, train, and test feed-forward neural networks, what I want to understand now is how do feed-forward neural networks understand data? What exactly are they understanding? Because a lot of text says that the various layers they they extract features from the data, and then each subsequent layer also extracts various other features. But from my point of view as the programmer, all I'm seeing right now is just the numbers. I want to get a better understanding of exactly what each layer is doing, and I'm not really sure how to get a better understanding of that. Like, it's not enough for me to just conceptually understand that, oh, each of these layers is probably extracting some features. What I want to do is I want to be able to pinpoint that, hey, this layer is extracting these features, that layer is extracting those features, and hopefully I want to be able to visualize what each layer is seeing. Understandably, this becomes a little bit complicated when we have kind of flattened the data. So the pixels, it's just like it's a row of colors. We are not looking at an image anymore. We are looking at slices of an image, or slices of one image that have been laid out linearly, or one after the other. So it kind of loses all its meaning in terms of in like visually. It kind of loses all its meaning, and I think once we get into convolutional neural networks, they kind of explored this concept. I think they call it spatial something, spatial meaning. I forgot exactly what the term was, but convolutional neural networks, they do solve this one problem that feed forward neural networks have, which is that the way that we process the information of the way that we process the data of an image before feeding it into the neural network, it kind of destroys the meaning. Okay, I'm gonna pause real quick because in like the next 30 seconds, there's gonna be an ad break. So I'm gonna start the ad break right now, and I'll take a little hydration break, and I'll see you guys in 30 seconds. Where is that ad button? Here it is. Okay. I'll see you guys in 30 seconds. Okay, welcome back. So, like I was saying, um, so once we get into convolutional neural networks, we learn that, or well, we will learn because I've already read up on convolutional neural networks to a certain extent. I haven't really dived deep into it, but I have read up on the theory and I kind of understand the idea behind convolution. But something interesting that I remember reading was that convolutional neural networks, unlike um, unlike feed forward neural networks, they don't destroy the meaning of the pixels. Like the pixels, they have some meaning. Um, how do I even say this? The group, or let's say a group of pixels that are together, they have some meaning because you're able to get some information out of them by what that group of pixels represents. But when you flatten it, you kind of destroy that meaning. Now, this brings up an interesting point that, or an interesting question, which is if flattening the image into an array of values destroys the spatial meaning, or it destroys the meaning that a specific group of pixels within that image would have had, then what kind of information is a feed forward neural network able to extract out of this array of pixels, or out of this image whose spatial meaning we have destroyed? What was it called? What was, hold on, I need to look this up because I keep saying spatial meaning, but it was something spatial. It was an interesting term that I had seen, and I've seen it used multiple times. So I'm going to look at this. Also, I need to remember this person's name because the other day I had to take my dad for an appointment, and while we were in the waiting room, I usually read up on deep learning stuff when I have like nothing else to do and just a phone with me. So I read up on deep learning stuff. Usually I try to come to Medium to read up on this stuff. And fortunately I didn't close this browser recently, and I had found this person's account. Their name is Sasireka Kota. I remember coming across this person's account, I think during the last stream as well. I think since the last stream, I haven't closed this specific browser, and this person apparently has. So okay, the deep learning. So this is a this is one of the multiple series that they have on their profile. This one is called Deep Learning Basics, and this is part 8. Part 8 is what's going into convolutional neural networks. But if you go further back, I think this was part 1. This was part 1. This already, it starts going into NLP stuff, which is super interesting because like it goes into, I think it goes into embeddings at some point as well. This is part 1. Uh let me scroll down here so I can show you guys part 3 and 4. And okay, so part 7 is feed forward neural networks. Oh, this is good. Okay, so for basic like ML and data science stuff, you can probably look into this series, which is Fundamental Tasks of AI. I am actually going to be looking into this as well because a long time back, like when I was getting into data science and I was like super big into it, I was like, dude, I want to try and find patterns in data. And well, I just kind of got distracted with other stuff and didn't end up going too deep into data science specifically, but I did end up using data science stuff in deep learning. I do want to go back to doing data science stuff as well. But yeah, okay. So, part 6 talks about something called a skip-gram model. Then we have something here, word embeddings. That's in part 4. In part 2, they're explaining perceptrons. Where's part 3 gone? I think it was somewhere. Oh, these are the pinned ones. How do I see all of their stuff? There has to be like a button or something like that. Oh, I think it was loading more stuff. Uh, yeah, how do I see more of their stuff? Oh, here's another. Oh, wait. Okay, so part three is a discrete representation of text, and then they also go into word to vec. So there's a whole bunch of like NLP stuff that's covered in this series. I think they might cover other stuff as well, and I'm also glad that I saw this thing. Where was it? Here. Fundamental tasks of AI. So here they, in part one, they look into classification and regression. The interesting thing is, I've looked into regression, more specifically linear regression, but I never got into the classification side of things. I never tried using a linear regression model for classification. Actually, I don't know. Would that even work? I think that should work. De- Depends on how you would use it, though. And also, even in linear regression, I specifically looked at linear regression models using what was that? Ordinary least squares to calculate the line of best fit. I never looked into stuff like decision trees. That's a pretty interesting. I think this is covering decision trees. I'm not sure, but yeah, decision trees are also an interesting concept, dude. This is a great thing about data science. Once you look into data science stuff, there's tons of stuff for you to explore, and a bunch of this stuff helps you explore data. That's the interesting thing about it. Okay, so this goes into clustering, and I have specifically only explored k-means clustering. I haven't explored the other stuff. I do wanna explore the other stuff as well. But yeah, I think this is gonna help me because what I want to do is get an understanding of, because okay, what I was doing previously is I would go through the scikit-learn docs, and I would see like a whole list of various, or well, I would see a bunch of different sections, and in each of those sections they would be mentioning various algorithms that help with various data science things. So I would read some of those descriptions, and whichever seemed more interesting to me, I would just pick one of those techniques and start learning it. What I could do here is, here I'm going to be exposed to a bunch of different like methods and stuff as well. So I don't know how many parts they have for fundamental tasks, and the interesting thing is this is all from 2023. This is like 2 years old, or 1.5 year old content. But yeah, okay, this is for me to read. So, oh yeah, I was supposed to be looking into the spatial thing. Let me look up the word spatial here. So this mentions spatial domain, spatial invariance, spatial dimensions. I forgot what it was saying, something about spatial, and I think that's basically how you describe what what a group of pixels means. I think that's what you call spatial information, basically. Just a second. If there's something else convolutional neural network related, I think I'll open that up, and I can't remember what it was. It was something spatial. So give me a second while I look into that, and then we can get back. Um, Spatial hierarchies. Okay. Read the full story. Okay, so we are not doing that. Give me a second. Yeah, so we'll look for something else. Spatial. Okay, this mentions spatial dimensions. Oh, you know what? Here's what I'm gonna do. I already have this thing open. So I'm gonna load up Sonar Pro just so I get a shorter answer. I remember reading a bunch of um, articles on the basics and the theory of CNNs. Let me be more clear. Convolutional neural networks, CNN, and a bunch of them mentioned the term spatial and how CNNs compared to um, FFNNs preserve the spatial information slash meaning in an image since they don't flatten the image. Help me understand this thing about spatial. Okay, what does spatial mean in CNNs? In the context of convolutional neural networks, spatial refers to the two-dimensional, sometimes three-dimensional arrangements of data in an image. Specifically, how each pixel or voxel has a fixed location relative to others, forming meaningful patterns or structures across width and height, and depth if relevant. In other words, spatial information is the knowledge of how features in data are arranged and related within the space of the input image. How CNNs preserve, okay, we're not going to go into this part. We'll go into this part after we get into CNNs. Now, here's what we're going to do. I'm gonna craft a prompt. I'm gonna craft a prompt which I'm going to use every single time that we are doing this research, because I'm not going to finish doing the entire research today. But just so I'm getting somewhat consistent information, I want to use the same prompt regardless of what machine I'm doing it on and regardless of which system I'm doing it on. So right now we're gonna create this prompt, and then I'm gonna copy it somewhere, and then I'm also gonna type it out on my other system because I often read DeepSeek stuff, or I often use DeepSeek on another machine as well. It's not necessarily always on this machine. In fact, I mainly use DeepSeek on this machine while streaming. Otherwise, it's pretty much always running on the other machine. Speaking of which, I should try running DeepSeek locally because I believe it is open source. It's open source, but I don't know if I have to. Um, I don't know if the weights are behind some kind of wall, not necessarily a paywall, but some kind of wall. I don't know if that's the case, because I remember back when Llama had been released, and I'm talking about like the first version. Then in subsequent versions, they kind of changed their licensing requirements and stuff like that. So the idea was that it's open source, right? But in order to get the weights from them, you would have to fill out a form. It was still open source, it was still available, but I think for their own data collection purposes, they wanted to know who is getting the weights. They probably had their reasons for wanting to know who's getting the weights, but my point is getting the weights wasn't necessarily as simple as just downloading it off of, I don't know, Hugging Face or something. Even if it was hosted on Hugging Face, I don't remember if it was hosted at the time. This is again the first llama we are talking about. Actually, was it called llama at the time? I don't even remember that. I don't remember if it was called llama or something else. But yeah, okay. The first llama that had come out. Um, what was I saying? Yeah. So my point is, I need to check if there's some kind of wall behind which these weights are. Not necessarily a paywall. If it's open source, then there's not going to be a paywall. But I need to see if there's some other kind of wall that it's behind. And then if it's not, then I will download the weights and the model as well. If Transformers has an implementation of DeepSeek, I don't think I need to implement the model myself. Besides, I don't think, given my very basic knowledge of deep learning, I don't think I can implement such a complex LLM like DeepSeek. So I'm not gonna bother trying. But yeah, I need to see if Hugging Face Transformers has an implementation of DeepSeek, and if it does, then I need to see if the weights are just readily available, or if there's some kind of thing where you have to accept some kind of agreement or whatever, or if you have to agree to share your information with them, because that's the thing on Hugging Face. Sometimes models or data sets, they are behind some kind of gate, and the gate might not necessarily be a paid it might not necessarily be a paywall, but this data is still, it's gated in some way. One of the ways is they'll ask you for access to your information, more specifically probably your username and email that you're using that Hugging Face account from. Though this brings up an interesting thing that I'm yet to look into. Once I've accepted something, once I've accepted the terms, once I've accepted to share my information for a certain data set or a certain model, how exactly am I going to reflect that when I'm trying to run, when I'm running HF transformers from a Kaggle notebook? My guess with this is using some kind of token and then supplying that token along with whatever request I'm sending. But yeah, I need to look into how I would go about doing that, because my guess again is just that they'll give you a token, and through that token they'll be able to find out whether you have access to this model slash data set or not. Okay, so let's start by crafting this prompt. I don't know if we are going to be reading the prompt because, like, and this is completely my fault. I started the stream late. That is completely on me. That is my fault. I'm hoping I get to stream tomorrow as well. Hoping. Let's see though. I don't know. But yeah, okay. So I have been learning about feed forward neural networks, FFNN. I have learned how to build, train, and test FFNNs. I've used things like, or let's say I've come across concepts like, no, I've learned about concepts like um, hidden layers. Maybe I don't need to capitalize it. Hidden layers, neurons. Sorry, zoned out. Okay. By the way, there's a fun project that I have planned. I'm not going to talk about it too much, but there's a fun project that I have planned, and I kind of want to do it on stream. Um, one, because I want to do it on stream, but also because I'm hoping to be able to make a YouTube video out of this and then upload it later once the project is complete. Okay. Uh, yeah. So more on that later. I've learned about concepts like hidden layers, neurons. What more? What more? Let's say, etc. I've built the network using linear layers, ReLU layers. Was there anything more? No, it was mainly linear and ReLU layers, and at the end, the output was actually. Did I run it through a softmax? No, cross entropy loss implicitly involves softmax. So, and in the end, I calculated the loss using cross entropy loss. Sorry, zoned out. Okay. I calculated the loss using cross entropy loss. What else? I'm because I'm trying to expose all of the stuff that I know about feed-forward neural networks. Um, these are the specific things I know about FFNNs. I haven't looked into other possible types of layers and functions. So for the time being, I want to do my research keeping my existing knowledge in mind. Now, I have a few questions and doubts regarding FFNNs. Actually, maybe I could like number the questions. I understand. No, FFNNs flatten the input image data which destroys spatial meaning in the data. Despite this, how exactly are they able to extract features from the data? Two, I'm trying to understand what exactly each layer, what exactly each hidden layer in the network is extracting. I want to visualize what each layer is extracting. Three, we say, no, is each layer basically just extracting features? And then four, what more? Because I wanna list out all of the doubts that I have. Let's look at a diagram of yeah. So we have the input layer. Oh, nonlinearity. Yeah. Um, help me understand the idea of, oh, I missed an S. Understand the idea of non-linearity and why we need functions like ReLU. I understand that they introduce non-linearity, but I'm trying to get an understanding of what exactly that means and what it would mean if we didn't have non-linearity. What else? What else? I would also like to understand how the data changes and what it turns into as it goes through each layer of the network. You know what? For the time being, let's hold on to let's copy this. I'll add more questions as yeah, okay, hold on. So while this is being answered, let me just paste this question here so I can then later type it out elsewhere and then I'll have something to copy each time I want to revisit this conversation because the next time that I type this exact same thing uh, to DeepSeek, I'm probably going to get a slightly different answer. I'm still going to get the same accurate information. It's just that it's going to be answered in a different way, presented in a different way, and maybe there might be a few bits of information that are either different from well, no, that are placed, I should say, placed differently than the previous session, or they might just be missing. That doesn't make either of the answers right or wrong. It's just that I want those extra bits of information that are being presented as well, along with the main sort of meat of the message, quote unquote meat. Okay, let's try to tackle these questions one by one. I'm a bit new to neural networks, so I might need to think through each point carefully. Starting with question one. Um, feed-forward neural networks flatten the image, the input image data. Oh, I should also hold on. I just remembered something. So here's what we're gonna do. Okay, we're gonna refresh. Um, I need to mention what I used. Um, these are the specific things that I know. Okay, all right. Uh, Also, I used PyTorch, and the specific and I specifically built a classification neural network. I built two of them, one to one to classify images from the MNIST dataset, and one to classify images from the fashion. What did I hold on, from the fashion, from the fashion MNIST dataset. Okay, let's copy this. Give me a second. Let me get up and like stretch and stuff. Okay, so good bit of information here. Let's start. Okay, let's tackle these questions one by one. Starting with question one: how do feed-forward neural networks extract features even after flattening the image and losing spatial information? I remember that when you flatten an image, you're converting the 2D pixels into a 1D array. So spatial relationships like nearby pixels are no longer explicitly represented, but feed-forward neural networks can still learn patterns through the weights in the hidden layers. Maybe each neuron in the first hidden layer connects to all the input pixels, so it can detect things like edges by combining certain pixel intensities. Even without the spatial structure, the network can still learn which combinations of pixels like edges or textures are important for classification. But how exactly? Maybe through the training process, maybe through the training process, adjusting the weights to activate on certain patterns. Oh, you know what? That brings up another good question. So I'm gonna write. I need to stop interrupting it. So I'm just gonna write out the additional question here. What exactly is neuron activation? What does it mean for a neuron to activate? Uh, how does neuron activation affect the data that is being processed, what is the result of neuron activation? What I'm assuming here is that neuron activation in this case is basically just that the data is being allowed to be passed through because yeah, I think so. I think that's what it is. Because the neuron activation is done through after the thing passes through ReLU, right? Or am I understanding neuron activation wrong in this case? Because my way of imagining it was um, so we have ReLU, right? The data is passed out of the neuron or out of well, yeah, the data is passed out of the neuron and fed into ReLU, and anything that is less than zero, so anything that's a negative value, becomes zero. So that doesn't get passed through. Otherwise, it just passes the value. So basically, anything that's positive, it gets passed through. And that was my understanding of the neuron activating in this case. I need to figure out if my assumption there was right, and then I need to figure out what exactly it means for the data and for the final result. Okay, where was I? But how exactly? Maybe through the training process, so and so, so and so, so and so. Where did I read the term activate? Oh, I think I saw it here, neurons activation. I thought I read it somewhere here as well. But how exactly? Maybe through the training process, adjusting the weights to activate. There you go. Okay, that's where I read it. Adjusting the weights to activate on certain patterns. But isn't that inefficient compared to convolutional neural networks, which preserve spatial info? Moving to question two. Visualizing what each hidden layer extracts. I've heard about techniques like activation maximization, where you find input patterns that maximize a neuron's activation. Back up. Visualizing what each hidden layer extracts. By the way, so far, in terms of visualization, I wouldn't say the best, but something that I did find that was incredibly useful is this neural network playground set up by, I don't remember set up by who. It's set up by a team, I don't know, at Google or Microsoft, one of these two. But it's by TensorFlow or Keras. I'm not sure. Let me hold on. Let me show you guys what I'm talking about. I don't think I'll run the thing. I don't think I'll run the training process, but I just want to show you guys the playground. Neural network playground. TensorFlow. Okay. Right. So this is the neural network. This is a neural network, and you can. There's a bunch of different things that you can do here to kind of customize the network. Like you could increase the number of hidden layers. I don't know what the limit is. I haven't like tested that out. But yeah, you can increase the number of hidden layers. You can also control the number of neurons in each layer. I don't know if it's different, but yeah, okay. You can have like different number of neurons per layer. Um, you can also control the number of input points, input features, I guess we can say. Yeah. There you go. The number of you can control the number of input features. I think this is the output layer, so you can control the number of um, well output features as well. You can also control the ratio of training to test data. You have four different data sets here, which have been visualized, so you can see some meaning in them. Then there's noise as well, which I haven't experimented with this. I haven't had the need to include noise, but like, well, no, okay, no, hold on. I say need as if I've been working on feed forward neural networks. No, I haven't come across um, tutorial material that has used noise so far. I have come across tutorial material that might introduce data that's outside of the training data set, but then that's basically just test data. Okay, anyways. And then there's batch size as well, which um, I'm assuming batch size here means okay. So I was gonna assume that batch size was talking about like the when you're testing the model, because like you can pass in a you can pass in like a group of data and then calculate the loss based on that group, which we did with our feed forward neural network as well. It was batch size of 64. So we used a batch size of 64 while was it specifically while testing, or was it also during training? I think they were used in different ways. I don't think they were used in the same way. I can't remember right now. I'm gonna have to go back and look at the training code. But yeah, you can do that, and then you have this thing here as well, which allows you to visualize I believe it's the output. Oh, you can hover over these to kind of visualize them. And this, I believe, is showing you the data, the data set itself. Then there's a couple of other options for customization, and oh, up here you have learning rate, which is by how much you want to change the weights in each epoch. Um, then you have the activation function, which activation function you want to use. In our case, so far it's just ReLU. Then regularization methods. I haven't looked into regularize. This word, I hate saying this word. It is not easy to say. It doesn't flow very easily for me. We haven't looked into regularization methods yet. I think L2 is one of them. Yeah, L1 and L2. And then regularization rate and the problem type, classification or regression. So there's a good bit of like customization that you can do here, and I'm going to be doing this as well, just so I can hopefully get some kind of understanding of how the neural network is perceiving the data and how the neural network itself is seeing the data. That being said, let's get back to this. Okay, moving to question two. Visualizing what each hidden layer extracts. I've heard about techniques like activation maximization, where you find input patterns that maximize a neuron's activation, or maybe visualizing the weights directly. For example, in the first layer, the weights might look like edge detectors, but deep layers might capture complex more what might capture more complex features. Deeper layers might capture more complex features. But how do I actually do this in PyTorch? Maybe by accessing the weights of each layer and plotting them. For convolutional layers, I never actually thought about that. Visualizing the weights of the layers. No, visualizing the weights of each neuron in the layer. Okay, maybe accessing the weights of each layer and plotting them. For convolutional layers, you can visualize filters, but for feed-forward neural networks, since it's fully connected, each neuron sees all the inputs. So the first layer's weights could be reshaped into the input image dimensions to see what patterns they detect. Okay, okay, hold on, wait, shit. Yeah. Question 3. Are layers just extracting features? Well, each layer applies a transformation, linear plus nonlinear, to the input data. So each subsequent layer builds on the previous ones, combining lower level features into higher level ones. So maybe the first layers detect edges, then next layers combine edges into shapes, and so on. Sorry, zoned out. Okay. Uh where was I? And so on. But in a feed-forward neural network, since it's fully connected, maybe the features are more global rather than local. I'm not sure what that means, but there's something to be explored there. Global versus local features. There's something to be explored there. But for image data, this might not be as effective as CNNs. So each layer is indeed extracting information, extracting and transforming features, but the nature of the features depends on the architecture and data. Nonlinearity. With ReLU, if you if we only had linear layers, the whole network would be a linear transformation, which can't model complex patterns. ReLU introduces nonlinearity, allowing the network to approximate any function. You know what? I got the next question. Hold on. Question 7. Um, it is said that nonlinear functions allow the network to learn complex patterns. What exactly does it mean for the network or a layer to learn a pattern, simple or complex? How do I visualize the patterns that the network or a layer uh, is learning? That's a good question. Okay. Um, Wait, this is interesting. ReLU introduces nonlinearity, allowing the network to approximate any function. Universal approximation theorem. I need to look into that. Okay, without nonlinearities, even multiple layers would be equivalent to a single layer. So nonlinearities let the model capture more complex relationships in the data. For example, ReLU allows the network to have piecewise linear functions, enabling it to model more intricate decision boundaries. Okay, question 5. How data changes through layers. Initially, the input is a flattened vector. The first hidden layer applies a linear transformation, weights and biases, followed by ReLU, which zeroes out negative values. Okay, so the data becomes a combination of input features and nonlinearity. Okay, each subsequent layer does the same, potentially capturing higher level abstractions. Okay, I have another good question. What exactly does it mean um, for a layer to capture low level features, high level features. What else did it say? Low level abstractions and high level abstractions. Is there any way to visualize all of this? Okay, where was I? Each subsequent layer does the same, potentially capturing higher level abstractions. For classification, the final layer outputs logits, which are converted to probabilities via softmax. So each layer transforms the data into a new representation that's more useful for the task. For example, MNIST might go from pixels to edges to digit parts to whole digits. Transforms the data into a new representation. Okay, okay. Wait, but in F in feed-forward neural networks, since it's fully connected, each neuron in a hidden layer has connections um, to all activations. I just realized that going down. So far, this is just a thinking process. We're gonna go down and see the actual answers as well. Okay, okay. You know what? No, this is giving a good bit of information. And this is kind of why I like seeing the thought process when it comes to doing research. I like using models like DeepSeek or other reasoning models because they show you the thought process, and through the thought process, you can get a fair bit of information. Where was I? Was it question five? Yeah. Okay. Wait, but in feed-forward neural networks, since it's fully connected, each neuron in a hidden layer has connections to all activations from the previous layer. So each layer's output is a nonlinear combination of all previous features. Wait, let me run that back. Um, since it's fully connected, each neuron in a hidden layer has connections to all activations from the previous layer. All activations. So basically everything that passed through ReLU, right? Anything that isn't zero. So each layer's output is a nonlinear combination of all previous features. I have an idea. I have an idea. I want to write this down real quick. Uh, deep learning idea for later. Okay, so what was the idea? Um, visualize. Um, hold on. At the start of training, visualize how. Okay, what can we do? Visualize. Bar graph, histogram. That's another one we can do to sort of group the value. But like, if I group the values, that'll further destroy any meaning that the thing might have. Maybe let's not do a histogram. Um, what is the other one called? There was one that I'd seen used for analyzing audio. But not just audio, like other stuff as well. What was it called? A stenograph? Stenogram? No, what was a? Hold on, I need to. What is it? What is it called? No, stenography is it's a court related thing for creating transcripts. So that's not what I'm looking for. I'm also not looking for the term steganography because that is hiding information within data, or more specifically, I think within images. That's not what I'm looking for. I'm also not looking for histogram. What exactly was it? Wait, let me see. Let me take a look at all the Seaborn visualization things that are available. Maybe I might find it in that. Because what I'm looking for, it kind of looks like a heat map, but I'm not sure. Oh, you know what? Wait. So since this is used to visualize audio, visualizing audio data using using what? What exactly am I trying to use to visualize? I think was it SciPy? I think it might have been SciPy. SciPy audio. Yeah, SciPy has an audio section. Maybe in there, there might be a way to. Uh, what was it? Display? No, I think I need to ask. Hold on. Instead of guessing, let's do this. Um, Back when I was learning about data science and data visualization, I had seen a method whose name sounded similar to steno stenography or steganography. Did I spell that right? How do you spell steganography? Hold on. Wait, is it not called steganography? Yeah, it's called steganography. Did I spell this wrong? Steganography. Yeah, no, I think I spelled it fine. Okay, whatever. Similar to stenography or steganography, but it wasn't either of those. Uh, this method has also been used to visualize audio data, and it kind of looks like a heat map, but it's definitely not a heat map. Any idea of the visualization method I might be thinking of? Spectrogram, that's what it was. Hold on, hold on. Yeah, yeah, it's a spectrogram. That's what I was looking for. It says, based on your description, a visualization method that sounds similar to stenography or steganography is commonly used for audio data and visualizing and visually resembles a heat map, but is not exactly a heat map. The method you are thinking of is most likely the spectrogram. What is a spectrogram? A spectrogram is a visual representation of the spectrum of frequencies in a signal as it varies over time. It is widely used in audio analysis. Oh my God. Encoders. Hello, hello. Welcome to the stream. Thank you for the raid. Encoders and raiders, welcome to the stream. Hello, hello. How's it going? How was your stream, encoders? Thank you so much for the raid. Appreciate it. What's up, guys? I'm Dem Keys. Welcome to the stream. I do study streams, and I'm super interested in data science and machine learning and deep learning. And lately, we've been doing a whole lot of deep learning. Today, actually, we are trying to do research on how exactly feed forward neural networks understand data and how they understand how they transform, how each layer in a feed forward neural network transforms the data. And I want to see if there's a way that we can visualize what exactly the feed forward neural network is learning. Give me a second. Let me give encoders a shout out. Encoders. There you go. Go check out encoders. Um, yeah. Go check out encoders. Thank you very much, encoders, for the raid. Appreciate it. What were you guys up to? We were talking about the geometrical intuition of linear algebra. We ended with infinite dimension vector spaces. That's crazy. That's also super interesting. Like, yo, hell yeah. We are currently so okay, right before you rated, a couple minutes before you, and that's super important for wait, really? Okay, then I'm going to look into this as well. We were talking about the geometrical intuition of linear algebra. We ended with infinite dimension vector. You know what? Okay. So I know that in deep learning, you do end up with like multi-dimensional data, and it's way more than two, three, four dimensions. And especially when you go into stuff like NLP and embeddings and stuff, then you have like what, I don't know, 50 hundreds of dimensions. We're going to get into that later. Yeah, I'm definitely going to be getting into that once I have a better understanding of um, feed forward neural networks and convolutional neural networks. Eventually I will be getting into NLP as well. Also, Asher, thank you very much for the follow. Appreciate it. Before you guys came, just like minutes before you guys came, I was trying to remember a term for visualizing specific types of data because I'd gotten an idea for visualizing what? Shit, I lost my train of thought. Hold on. It was okay. So I'm trying to understand how. So I understand that each layer in the neural network extracts features from the data, right? But I'm trying to understand exactly what kinds of features each layer is extracting. The issue is it's not as simple as visualizing an image, because if it's a feed forward neural network, we have already flattened the data, right? So we've kind of destroyed any dimensionality it might have. So the only way that we can visualize the data itself is by plotting it on like some kind of graph, some kind of like bar graph or something. But I want to see if there are other ways to visualize what exactly each layer is extracting. And there was also the concept of like, okay, the ReLU function, which is usually after each linear layer. The ReLU function is for introducing nonlinearity into the calculation. So this way, the neural network is apparently able to learn complex patterns. I want to be able to visualize those complex patterns as well. It just seems kind of complicated to visualize what exactly the neural network is learning. More specifically, what the feed forward neural network is learning, because I need to find a way to get a graphical representation of these numbers. So far, that's what we are exploring, and I've been getting different ideas for it. And I've also been crafting this prompt that I'm going to use each time that we are doing research on trying to understand how the feed forward neural network understands data. Um, oh yeah, like I was saying, shortly before you guys came, I was trying to remember this thing. I couldn't remember the word spectrogram. That's what I was trying to remember. I want to also visualize this data on a spectrogram. No, it's a spectrogram. Okay, okay, I need to remember that. So, where was I here? At the start of training, visualize using a bar graph or a spectrogram, or etc. Any other method that might work. Maybe, dude. Okay, what if I'm able to? No, I can't. I was about to say, what if I can visualize it using a heat map? But then a heat map would also, to a certain extent, require, at the very least, two-dimensional data. Okay, let me add it to the list, and then maybe later on I can see if there's a way to visualize. Okay, so at the start of training, visualize. What are we visualizing? It was something to do with each layer, each hidden layer. There was a specific thing that there was a specific thing. Was it the result of each layer? I think so. Yeah, yeah, yeah. Okay, so because each layer is gonna have, like, the output is gonna be, it's one value, isn't it? And then that gets, no, it's not one, is it? Yeah, yeah. Because then the entire layer then makes up. Wait, give me a second. For this specific purpose, I've drawn out a sort of visualization. I've drawn out a sort of graphical representation on a whiteboard so I can remember. Yeah. Okay. So in each layer, we have, for each layer, we have, in each neuron, in each layer, we have a weight matrix which has the same number of features as the previous layer. Yes. We have a weight matrix which is the same number of features as the previous layer, but then would would the layer be outputting a single, we can test that out right now. I'm just having a tiny bit of trouble just visualizing this because right now I'm kind of visualizing something else. So let me run this real quick and then we'll create a sort of, we don't need ReLU here, we just need the input. Yeah, no, you know what? Yes, yes, it does output just one value, but then because there's multiple of these, so it becomes, um, because there's multiple neurons, so it becomes a matrix. Otherwise, I believe it would be one value for each neuron, that is. Let this finish running, and then, oh, is it done? I think it's done. Okay, right. So let's create an input tensor. Tensor, let's say 0.2 and 0.5. I think that should be good. And then linear can be nn.linear. It takes in two features and gives out four features. Then our result would be this, and we pass in the tensor, and then let's print. Right. Okay. Um, yeah, yeah. So for each neuron in the layer, we have one value. Assuming assuming it is assuming it's one-dimensional data, because this is not multidimensional. Assuming it's one-dimensional data, we will have one value per neuron. Now, why was I doing this? Yes, I was doing this to be able to visualize. Okay, at the start of training, visualize the values. Yeah, the values of each hidden layer. So each neuron in a layer as some sort of graph. Then, as training progresses, every, I don't know, 100 epochs, or every 1,000 epochs, let's say every 100 epochs, because otherwise it's going to be a lot of images that we are looking at, because this is all, it's all going to like be visualized as a graph, and then each graph is going to be like there's going to be like rows of graphs. So with our where was it? Here, with this simple neural network, I think, so we don't need to visualize. You know what? Okay, we can also visualize the input data. So then we can have like rows where each row represents what the values look like every 100 epochs, I think. Oh, wait, I missed some messages. I'm back. I was saying that in general, linear algebra is super important for neural networks, but also infinite dimension vector spaces and finite dimension subspaces are super important to understanding function approximation. For example, you can work. You can work with an abstract space of words with infinite dimensions by approximating that space to r multiplied by n, not multiplied, r to the power n, making calculations and then going back to the infinite dimension space of words. That's basically what LLMs do. They predict the most likely next word. The calculations are done in a finite dimension space, and then you return to an infinite dimension space to give the response. Can work. Sorry. Yeah, that's fine. Typos, dude. I have typos like all the time. It's one of the reasons why I hate typing um on the phone. I love typing on the keyboard, but like even on the keyboard, sometimes I'll make errors. But on the phone, it's like typos all the time. But yo, I'm super interested in this. Definitely. And I'm glad that I'm glad that this kind of connects with NLP and LLMs, because I was planning on going towards LLMs a little bit later as well. Because my plan right now is to get an understanding of. So I wanted to start with feed forward neural networks. Then I wanted to go towards convolutional neural networks, because I want to do some computer vision stuff as well. And in general, I just wanted to learn about convolutional neural networks. Um, then I want to kind of touch recurrent neural networks, maybe not go too deep into it, but like just get an idea of what's going on there. And then I wanted to go into transformer based neural networks. And I believe, yeah, I mean, NLP does tie in with that as well, because transformer based neural networks do get used for NLP purposes as well. So eventually I'm going to kind of like get into get into this. But this is super interesting. This is actually super interesting. I'm gonna read up more on, like, specifically the stuff that you said. I'll read up more on it. Also, once again, thank you very much for the raid. And Alex Angel, thank you for the follow. Appreciate it. Welcome to the stream. Uh, I'm currently, what was I? Yes. This is what I was, as some sort of graph. So this is one of the ways that I'm trying to. This is one of the ways that I'm trying to visualize possibly what the neural network might be learning, or what might be changing within the neural network's understanding as training progresses. Maybe through that, I might be able to get some idea of exactly what the neural network is learning. Okay, encoders, you said a convolution is an operator that gets two functions as an input and gives you another function. Those functions are elements of an infinite dimension space. I read up a little bit on convolutional neural networks. It was a pretty new concept to me, and the way that they do the calculations is also kind of interesting with like the filters and stuff. Um, I'm gonna get into that. I'm going to get into that. That's actually the next thing that we're going to be getting into immediately after I've gotten a better understanding of, well, feed forward neural networks. I just kind of got hung up on feed forward neural networks because I didn't want to move past it without properly understanding. Because, okay, it's it's fine to understand that, yeah, this is a feed forward neural network. um, you can build this thing to solve classification problems and to solve, to a certain extent, regression problems. But I wanted to understand exactly what is going on within the network, how the number of neurons in a hidden layer can affect the output, what exactly is each hidden layer learning, and so on. Now, okay, I'm saying to do this every 100 epochs. What did the training data look like? Do I have that? No, that was in a different notebook. Okay, we could do it every 100 or every 1,000. No, actually, it's the number of epochs, right? It's the number of epochs, and in each epoch we're gonna have what, like the 64 things that are being iterated over. Okay, let's just say every epic, because I don't think I have more than what, 20, 30. Even if it's up to 50, we can have like a row of 50 images and then just kind of like visualize the entire thing. That would be interesting to look at. Every epoch, visualize the values of the input layer, hidden layers, and output layer. You know, I wonder if there's some way we could use other data analysis methods to sort of compare data from one epoch to another epoch, like how things have changed. I wonder if that would reveal something about what the network has learned. Because I have a doubt that what exactly the network is learning, like the specific features and stuff, I feel like they get spread out depending on, I'm not sure depending on what. I think they get spread out randomly, but like, because initially the neural network is initialized with random weights, right? And then we, throughout the training process, we slowly get it to a point where those weights help with properly classifying the data. So I wonder if what the neural network is learning, like what each hidden layer and each neuron in each layer is learning, is kind of like during different training sessions, you might end up with the features being in like different places. I guess we'll find that out once we actually learn how to visualize these things. Let's go back to what DeepSeek was saying. But in feed-forward neural networks, since it's fully connected, each neuron in a hidden layer has connections to all activations from the previous layer. So each layer's output is a nonlinear combination of all previous features. This might make it harder to interpret specific features compared to CNNs, which have local receptive fields. But through training, the network learns which features, which combinations of pixels, are important in distinguishing classes. The loss function guides the weights to adjust so the final output minimizes the error. For visualization, question two, maybe using techniques like forward hooks in PyTorch to capture activations. Hold on. What is this? Let me look into this. So we can hook these into certain events and then have something happen. Let me look at that. PyTorch forward hooks. Module.register module forward hook. Register a global forward hook for all the modules. This adds global state to the nn.module module, and it is only intended for debugging slash profiling purposes. Wait, let me bring it up here. This is interesting. I'm gonna look into this. Where where was it? Okay, PyTorch forward hook. Give it a second. All right. While this loads, I guess we can continue reading. Where was it? Where was I? To capture activations when passing an image through the network. Then for a given input, you can see how each layer's activations look. Or for a trained network, generate images that maximally activate certain neurons, which could give insight into what features they detect. Regarding question one, again, even without spatial info, the network can still learn statistical patterns. For example, certain pixels being high might indicate a certain might indicate a particular class. But since images have spatial correlations, the network might implicitly learn these through the weights. However, feed-forward neural networks are less efficient at this compared to convolutional neural networks, which explicitly model spatial hierarchies. Also, for question 4, without nonlinearities, the network can't learn nonlinear decision boundaries. Real-world data is often nonlinearly separable. So nonlinear activation functions are crucial. For example, classifying circles versus squares in a 2D plane would require a nonlinear boundary, which a linear model can't achieve. But a neural network with nonlinearities can. That's interesting. Okay, okay. In summary, each layer transforms the data into higher level features through linear combinations and nonlinear activations. Visualization can be done by inspecting weights or activations, and nonlinearities are essential for capturing complex patterns. The flattening in feed-forward neural networks loses explicit spatial info, but the network can still learn relevant patterns through training on flattened pixels. Let's address each of your. Okay, so this goes into like each of the questions individually. Okay, now hold on for a second. All right. Okay. So give just a second. Right. So here's what we're gonna do. Okay. I would love to continue the stream, but and this is completely on me. I started the stream late, so I was only able to go for this long today, which I mean, to be to be honest, like 2 hours, it's still pretty much the max that I usually do. But okay, uh, that's gonna be it for today's stream. Do stick around. If you're not able to stick around, that's perfectly fine as well. That's understandable. Do stick around for the raid. I'm raiding someone named Snowlex, and they are doing a co-working slash study stream. Encoders, once again, thank you very much for the raid. Appreciate it. Uh, Asher and Alex Angel, thank you for the follows, guys. Thanks a lot for hanging out. Hopefully, I'm able to stream again tomorrow. I hope so, and I hope it's a talking stream. But yeah, that's gonna be it for today's stream. I'm gonna continue reading this stuff and hopefully get a better foundation of being able to visualize what neural networks are learning. Rodo, thank you for hanging out. Appreciate it. That being said, I hope you guys have a nice day, and I'll see you all next time. Peace. Oh, you're encoders. Okay, okay. All right. I hope you guys have a nice day, and I'll see you all next time. Peace.